Hello, everyone. I'm Tianhan Zhang from Southern University of Science and Technology in Shenzhen, in China. Today, I'm very glad to have Professor Matthias Ihme to bring us the talk about the machine learning and its application in combustion area. Okay, let me introduce the speaker first. Professor Matthias Ihme is a professor in the Department of Mechanical Engineering and Department of Photon Sciences at Stanford University. He holds a bachelor degree in mechanical engineering and a master degree in computational engineering. In 2008, he received his PhD in mechanical engineering from Stanford. After being on the faculty of aerospace engineering department at the University of Michigan for 5 years, he returned to Stanford in 2013. He is a recipient of many awards, including the NSF Career Award in 2009, the OMR Young Investigator Award in 2010, and the AFOSR Young Investigator Award in 2010, and NASA Early Career Faculty Award in 2015, and Hiroshi Tsuji Early Career Research Award in 2017. His research interests are broadening on computational modeling of reacting flows, and the development of numerical methods and the investigation of advanced combustion concepts. So it's our great honor to have Professor Matthias in here. Now, our time is yours, Professor.
Thank you so much. Okay. All right. So welcome to the presentation. It is really a privilege to present, and I'm thrilled to have this opportunity here. The presentation that I want to give is on the topic of combustion machine learning. I want to touch on 3 different topics. The first one is provide a brief overview on different principles and see how we can utilize some traditional machine learning methods. I want to talk about progress and also provide some linkage of potential perspectives and open research opportunities. And before I do this, I certainly want to acknowledge my co-authors here. This is Wai-Tong Chung and Ashwin Mishra, who have contributed to this work. And before we do this, I want to just jump right into the key topic here, and this has to do with data. Where do we get data from? And as many of you know, is machine learning methods are heavily data-driven. If you have no data, then this notion of machine learning is somewhat limited. And if we are reviewing this, data has been prevailing in the combustion sciences and engineering. We started out very early on, even in the late 16th, 17th, and 18th century, where our community collected extensive databases of different thermodynamic properties that you're seeing here. I think many of you are very familiar with the phase diagrams with the transition boundaries and supercritical fluids, but also fundamental properties involving formation enthalpies, Gibbs free energies, and so on. This moves on with the traditional NASA tables, which are extremely popular for a wide range of numerical simulations, where we have now access to polynomials up to 7th, if not 14th order accuracy to describe very complex fluids. If we are looking lastly to chemical mechanisms, we are currently at a stage where we can describe fairly complex fuels at sufficient accuracy with extremely large and detailed chemical mechanisms that have upwards of several thousand parameters. Right, so this is essentially a manifestation of the availability of data, and we want to embrace this and see how we can utilize this. Moving on, not only do we have data for thermodynamic properties and characteristic fluids, but we can also think about the characterization of systems, system behaviors in the context of sensors and actuators. And a simple example that I pulled here from the literature is that current operational systems, and this includes gas turbines, automotive applications, power plant systems, and so on, are heavily equipped with sensors for various applications. This includes health monitoring, optimizing operating conditions, mass flow measurements, and so on. And a simple example is if you're looking to a cross-Atlantic flight or an international flight of a commercial aircraft, you're generating several terabytes of data at a very high acquisition rate. So this means this data can be utilized and incorporated in our corpora of data for data analytics. Moving on, beyond this, if you're looking to prevailing environmental impacts, most notable wildfires, which are prevailing here in the western part of the US, there are sensors in the form of satellites, observational data, and so on. And they're equally generating large amounts of data where we're getting aerial views over different fuel properties, vegetation, moisture, humidity. And this is, again, data that we can take advantage of for certain applications that is related to combustion applications here in the context of modeling, predicting, monitoring wildfires, and so on. So this is, again, another area. But most importantly, if you're also looking to simulations, this is really at the heart of our problem here. Simulations from direct numerical simulations, as well as large eddy simulations or high fidelity simulations. If you're looking to the accumulation of data over the last 20 or so years, this illustrated here, this is the size of the DNS data, really how many bits we are generating on an average rate. You're seeing that this continuously increased over the last 15 years. We're currently in a plateau for several reasons. But what it tells us is that we can take advantage of this data, and this is certainly several terabytes or petabytes of data that we have access to for data analytics. Right. So by and large, there is clearly evidence that data is available that we can embrace and that we can utilize. But what is the challenge? The challenge is really summarized here on the next couple of slides. The first thing that we're recognizing is, yes, there is data indeed, but this data is very diverse, right? It comes from different sources. And in many cases, if you're moving to fairly complex float configurations, which is illustrated here on this graph on the right, if you're looking to gas turbine combustors, really complex engineering applications, the data is sparse, right? So we have less detailed information. This makes it rather difficult to extend knowledge that we generated from canonical flow configurations to some of the more industrial relevant applications. Another issue which becomes prevailing is data access, and I will be talking about this later on. Yes, this data is there, but it's currently typically heterogeneous distributed, and accessing this data is somewhat limited, right? And the last aspect, which we cannot forget and really have to recognize, is that there is certainly a prevailing domain knowledge. Our combustion community has been driven by physical intuition, by expert knowledge, and we certainly want to embrace this and utilize this into our data analytics, right? Another challenge, and this really goes about this domain knowledge, is that traditionally, the description of thermofluid flows in the context of combustion, chemical reacting flows, and so on, has been driven by fundamental thermodynamic principles. This is illustrated here on the right-hand side. The governing equations that describe some of these turbulent reacting flows are very well established. We have access to these equations in nearly exact form. And we would like to take this knowledge and incorporate this to some extent into our data-driven techniques. Right? What is the limit of this? Of course, also we can write down this set of governing equations in exact form. We have to recognize that these equations are typically difficult to solve or experimentally to observe. Reason for this is that those equations typically span a wide range of different scales, both in time and space, as well as the equations contain a large set of chemical species, making this rather difficult to solve, right? And lastly, because we have some incomplete knowledge about some of the constitutive relations that we have to incorporate in this required modeling, right? And then we'll talk about this as we go along in this presentation. Okay, so then we can say, well, we have data, but we also have some existing knowledge. So how can we combine this in such a way that we can take advantage of this notion of combustion machine learning or data-driven techniques? And this is illustrated here on this graph. I have two coordinates. The first one is my available knowledge, and here you can really think about our physical understanding. And on the y-axis, I have available data, right? So in the absence of data, as I said, well, we can really rely on our domain knowledge, and we can construct physics-based models. And we have done this to some extent over the recent years quite successfully, I would say, right? In the absence of available knowledge, well, we can certainly resort to purely data-driven methods, but this comes with the expense that it requires very large sets of data, which is currently not accessible in this stage that we would like to see it, right? And as a combination of both, we can say, well, if we are certainly have a limited set of data, but still would like to require or introduce our available knowledge, we can introduce so-called knowledge-guided data-driven methods. And you can really think about this, that we are augmenting our data-driven approach by physical intuition or by domain knowledge in an attempt to achieve physical consistency, to improve the generalization, meaning in the absence of data, I can still rely on my physical principle. I can reduce the amount of data, and with this get overall improved performance of my machine learning techniques or my knowledge-guided methods. And what I like to do here in this presentation is I want to talk about different aspects, starting out with purely data-driven methods, show you some of the limitations, and move on to knowledge-guided methods, and see how we can augment and combine different methods as we go along. All right. So the questions and the overview of this presentation has the following outline. I first want to address some of the questions on how can we use combustion science and engineering, and how can we embrace machine learning advances into these methods. So I want to review a few machine learning methods. I want to talk about how we can leverage knowledge and data, and talk about applications for various examples. The second topic is addressing what are the unique challenges in applying machine learning to combustion. As I said, one aspect is the data sets, available data sets that we would like to use. How can we integrate domain knowledge? Other aspects are uncertainty quantification and the development of combustion-specific methods and techniques. Okay, so let's get started with some brief overview of machine learning methods. And before I do this, I want to just introduce briefly a definition. I'm sure many of you are very familiar with this. In the simplest form, we can consider a machine learning method as a computer-based algorithm that infers predictive models from data. And here I want to go that far and say in the absence of domain knowledge, right? So what we have available is we have available data, and from this you want to extract some sort of knowledge or information that we can then potentially apply to additional or related cases. In this context, learning is the ability of the algorithm to progressively improve the performance of a specific task by exposing additional data to this learning algorithms. We can typically categorize different machine learning methods for combustion, and here I want to use or follow a traditional classification. I'd like to think about 3 different categories of machine learning methods. The most common is the so-called supervised learning. So what I have is I have labeled data. This consists of input features and output data, and they are labeled, they are categorized. And with this, I can train a machine learning algorithm, which is denoted here by this box, based on the input and the output mapping. This is a traditional method, and more involved system or extended system is a so-called unsupervised learning method, where I don't have labeled data, and I'm really trying to infer knowledge from an available set of data. And the last algorithm or class of algorithms is in semi-supervised learning methods, where I have a combination of labeled and unlabeled data, and I want to learn from this through interaction with this environment. A couple of relevant algorithms are, in many cases, supervised learning algorithms are primarily used for classification and regression. I show you a couple of examples from this, and I illustrate here several algorithms. I will talk about a few of them, but certainly not all of them. Unsupervised learning is primarily used for clustering, for dimensional reductions. Examples are the principal component analysis, autoencoders, k-means, where we can use those methods to identify consistencies, correlations, or as I said, construct reduced manifolds. Few applications that are of interest are the representation of field properties, the parameterization of complex reaction diffusion manifolds. But I can also use this to identify rare events, irregular combustion processes, or use this in the context of generative models for subgrid scale models, for turbulent closure models, as well as for the construction of chemical mechanisms. These are but a few examples that are very interesting. And as I said, throughout this presentation, I will give you a few examples on how we can utilize these different methods. Okay. So then, what is a generic algorithm and how does it look like? For those of you that perhaps not familiar with this concept, I have here a schematic of such a generic supervised learning algorithm sketched out. What we have at the outset is we have a physics-based relation, and this notion of X and Y, this is essentially a set of data. So what you can think about for a simple thermodynamic system and combustion system, X is an input feature, and this could be certain operating conditions that I exposing temperature, pressure, fuel species, mass fraction, operating environments, and Y is an output and response of this system. And this could be a thermodynamic response function. This could be in system output, thrust, species, and so on. This is what I'm looking for. I'm looking for a functional relation that I denote by F that maps my input to my observations or to my output. Right? And I'm inferring this by measuring data, and this is denoted here by this set of data denoted by X and Y. And I have n sets of this distinct data. What I like to do is I now impose a set of hypotheses, which I denote by H here. And this could be polynomial functions. This could be functions which are embedded in my machine learning algorithm. And the question then is, which one of my hypotheses fits best this observational data so that I can closely approximate my physics-based relationship. And this is essentially in principle, an underlying principle of supervised machine learning methods. I'm trying to identify a hypothesis that best approximates my functional relation that is hidden in my data set. How do I identify this hypothesis? Well, I introduce an error measure. This could be a mean square error or some related loss function. I'm applying an optimization method where I'm trying to minimize my error out of this hypothesis set with respect to the measurements. And what I'm ultimately obtaining out of this is an optimal hypothesis. In our simplest form, we can think about this is essentially an output of a trained machine learning algorithm. So if you're thinking about a neural network, the ultimate optimal hypothesis would be essentially a fully optimized neural network where I'm adjusting the weights and the bias in such a way that I can represent this data. Ultimately, what I like to do is to apply this hypothesis or this machine learning model for new data or to new data, which should be sampled from the same set of the measured data. So they should come from the same notional distribution. I can then apply this to predict this for engineering applications or scientific discovery, right? In this context, this approach, this machine learning methods is quite different from a classical regression methods or least square fit, where here in this case, we are identifying an optimal hypothesis or a functional representation or polynomial representation, whereas a least square fit essentially dictates the underlying polynomial basis, okay? Well, let's look how this works and what are the challenges that we are facing. And a simple example that I want to consider here is flame sweep measurements for a methane air mixture at ambient conditions. I think many of you are certainly familiar with those problems. I'm plotting here phi as an equivalence ratio, and you're seeing this bell-shaped curve. What you're seeing here is experimental data for a wide range of conditions. If you count this data points, this is about 150 data. And what we like to call this problem here is how can we identify in machine learning methods that best approximates this set of data. And to do this, I want to consider a simple polynomial representation. The first form, I want to assume that I'm using a first order polynomial. This is essentially linear functions. This is my hypothesis. And what you're seeing right away is if I'm trying to approximate this distribution or this flame speed measurements with linear functions illustrated by this gray lines, you're clearly seeing evidence of underfitting, meaning that my solution has a very low variance, but extremely high bias, right? So as soon as we are departing away from the conditions that I'm selecting, I'm underfitting my curve. And this really means that my first order regression, or in this case, my first order polynomial hypothesis, is just not rich enough, not expressive enough to characterize this. What I can do is I can extend my polynomial order, in this case to 5th order regression. So I have 6 degrees of freedom in order to describe this complex function. And what you're seeing, yes, indeed, my bias reduces. I have a substantially lower bias, but I have substantially higher variance. And this is typically associated with overfitting. And here you're seeing already one hallmark of a number of machine learning methods. We have to be very careful on how we are constructing our hypothesis set. And this depends equally on the amount of data that I have available. Right? Now, what we can do is we can find a middle ground. We can, for instance, use a 3rd order regression. And there you're seeing that this is a good compromise between the variance and the bias. And with this, I'm getting an adequate representation of my experimental observations. And this is, again, one way where I can now identify an optimal hypothesis, or in trained machine learning methods, algorithm that represents this flame speed data. Right. Other algorithms that I want to briefly talk about is logistic regressions, decision trees, and neural networks. This is again from the same class of supervised learning methods, and I would regard them as fundamental methods or algorithms that essentially constitute a wide range of different applications here. Right? With relevance to combustion, I want to see on how we can learn from the different methods, what are their advantages, and how can we apply them for different combustion problems. So as I said, the first algorithm that is perhaps the most simplest one is a logistic regression algorithm. And what it is in the simplest form, it's a binary classification model. Right? So what I have in a set of input parameters or input features, I have a linear combination, which essentially weights the systems, and I have an output here. Since it's a classification problem, what I really try to do is I take a set of input parameters and map this to a binary output response function, which I denote by psi. And this is either 0 or 1. And this is an ideal problem for classification. Many of you have encountered classification problems for combustion regime characterization, for ignition identifications, and related problems. And here we can utilize this in a simple form. What I want to emphasize here is that I have a predetermined hypothesis. This is in this case essentially a sigmoidal function. It's an exponential decay. It's a very smooth function. And this essentially allows me to activate the solution. In the simplest form you can think about is that if I'm exceeding a certain threshold in this parameter in this response function, I can essentially activate this, and by this direct my output from in this binomial space. Right? The machine learning algorithm with this set of initial hypotheses then boils down to identifying this weights W and the bias B. And I can use this and can do this using a maximization or an optimization of a maximum likelihood function, which is illustrated here at the bottom. So the algorithms for optimizing this are, I think, reasonably well established. We can resort to existing libraries and tools, and this provides us one methods. Logistic regression, as I said, is quite powerful. I show you here 2 examples in the application to classification of irregular combustion events, where I can demarcate fairly complex combustion regimes. This is about an order of 500 experimental observations, and utilizing a logistic regression provides us one way here to demarcate different ignition regimes. They are associated with an regular ignition and an irregular ignition. And this provides us some, I think, very powerful tools. Beyond this, logistic regression is also extensively used for wildfire predictions. This here are some observational data from Preisler. I think this is an area up in Canada, where they're essentially using a logistic regression to predict fire occurrence and to enable fire risk assessment. And they're employing this with very good accuracy. Very large, extremely large feature set is utilized to make fairly reliable predictions on the fire occurrence. And I think this is certainly one really exciting outcome of using rather simple machine learning methods to get predictive information. There are several challenges of logistic regression, and this is really the reason that I want to start out with the simplest condition. First one is that our hypothesis is predetermined, so we use this sigmoidal function as an underlying foundational hypothesis. Another issue is that the feature space requires linear separability, making this rather difficult to apply to complex systems. With this, we can think about how would we extend this, and one direct extension of this is a so-called neural network, where we're using similar principles, but building this up to more complex systems. But before I talk about neural networks, I want to also introduce decision trees, which is a slightly different application where I'm using a two-dimensional parameter space or a multi-dimensional parameter space. And I partition this parameter space into hypercuboids that provide different characteristics of different classification problems. Again, in this form, it can be utilized as a classification problem. And I want to show you later on one example very exactly doing this. It enables us to represent fairly complex relationships between inputs and outputs. And I can, as one major benefit, use this in order to extract physical, meaningful information. And this is typically done in the form of a so-called impurity measure, where I can now associate physical information or interpretability to this decision tree. And I think this is one benefit that we have been using quite extensively so that we can extract physical knowledge from machine learning methods. Right. There are some challenges of this traditional decision trees. They come in the form that they are have some a certain variability, and we can overcome this by assembling multiple of those decision trees. This here is a schematic of such a system. Each one of this sets here is a particular decision tree. This is which is trained on a subset of this data, and ultimately we are combining individual decision trees or the outcome of the individual decision trees to obtain a final result. This is reflected by this class of random forests, and they take direct advantage of the strengths of the weak learners. I'm combining different or a large number of these weak learners, in this case decision trees, to assemble more complex systems. They overcome the issue of the large variance, and with this, they're not prone to overfitting, and they maintain the benefits of a classical decision tree. There are some, again, challenges, of course, if you're building up larger and larger random forests, more and more decision trees, the computational cost increases, and this is certainly something that have to keep in mind if we are assessing algorithms in this way. The last class of supervised learning algorithms that I want to briefly mention is a class of neural networks. This is a more generic platform or method, a framework of models. In the simplest form, we can think about a neural network to be an representation of a brain structure and how we are processing knowledge through this brain structure through dense interconnected neurons. I'm showing here a neuron, and you're recognizing already, well, this is a fundamental building block of our logistic regression, here in the form of a multi-layer perceptron. And by arranging different neurons, this processing units, in this hidden structure here or in this larger complex network, we can essentially process different levels of information in these hidden layers. And if you're increasing the number of neurons and layers, we're essentially ending up with a very complex and quite expressive neural network representation. Each one of these transfer functions consists of sigmoidal functions here in our simplest form, but we can use different methods. And this essentially allows us then to represent fairly complex functional forms or output mappings for different representations, making this quite powerful for combustion applications, but also for other applications. Beyond this, I mentioned this in the context of a so-called multi-layer perceptron. This is in traditional methods, which has been quite extensively used for the parameterization of reaction diffusion manifolds for combustion systems, chemical mechanisms, and so on. But beyond this, there's a wide range of highly specialized systems, and this is illustrated here on the right-hand side, taken from the Asimov Institute, where I just want to convey different methods or different neural network architectures that are specialized for certain applications. Most notable are convolutional neural networks that instead of operating on scalar data, they're operating on field quantities, and this could be in the form of images, flow field data. We have recurrent neural networks, which take information about the transient dynamics, and they are quite powerful for applications to dynamical systems, as well as graph neural networks, which provide, which gain increasing attention for unstructured data. Right. So with this, I think I touched on a couple of representative machine learning methods out of the class of supervised learning methods. And what we like to do is to see how they compare. And for this, I constructed a rather simple problem here. And this has to do with the ignition of an N-dodecane air mixture at a pressure of 20 bars. So what you're seeing here is my feature space. This, in this case, this is two-dimensional. I have initial temperature from 500 to 750 Kelvin, and I have an dodecane mole fraction. This is pure air on the left-hand side, pure fuel on the right-hand side. And I'm plotting here the temperature on the right-hand side, the formaldehyde mass fraction. And what we can do is, looking to this picture, many of you who have substantial expertise identify different combustion or ignition regimes. And what we like to do is we like to ask the supervised machine learning methods whether we can identify different ignition regimes. This has to do with low temperature ignition and the high temperature ignition. Okay? So what we can do now is we can take the set of data and sample and training set. This is illustrated here in these two columns. In the top figure, each one of these dots or the symbols means that I have a training data point. In this case, these are 2% of the learning data. And in this bottom column row, you're seeing that we used about 60% of the learning data. Right? Now, what you're recognizing here is the three different machine learning methods that I discussed: logistic regression and feed-forward neural network, which is essentially this multi-layer perceptron. And I have this random forest, which is essentially a combination of decision trees. Right? We're identifying three distinct ignition regimes. Blue is no ignition. This means our temperature is just too cold, too low to facilitate ignition. I can identify a high temperature ignition and a low temperature ignition. Right? So these are the different regimes, and we can characterize them directly from the data. Now, what you're seeing here is the different machine learning methods for small sets of data provide quite drastically different behaviors and response functions. And you're clearly seeing that this random forest and to some extent also the logistic regression lacks expressiveness, especially for small data. And we're typically encountering these very sharp transition boundaries that are not quite conforming to the observational data, right? By increasing the amount of data that I have available, you're seeing that both of the methods approximately converge. Certainly this neural network, because it's much richer in its expressiveness, provides improved accuracy over logistic regression. And we're seeing that you're comparing the neural network, random forest, and the support vector machine method. All of them provide some comparable results in the case that we have sufficient data available. An important aspect which is often neglected is what is the test accuracy and what is the computational cost associated with the training and with the utilization of the methods. And I want to briefly talk about this, that in many cases for very small data, methods, machine learning methods, which lack some expressiveness can provide some benefits here. And this is illustrated in this case. If you're looking to very small fractions of the learning data, you're actually seeing that the random forest can certainly outperform some of the other methods. And if you're increasing the number of data or the amount of data, you're clearly seeing that some of the deep learning techniques here in the case of this feed-forward neural network provides some incremental improvements over some of the more traditional methods, right? And this is, I think, a hallmark of some of the methods which just have more expressiveness and where this can accommodate a larger set of data, right? Test data, as I said, this comes with a price, of course. Neural networks, since they can be very large, very complex, they require typically more computational cost. And if you're thinking about engineering applications of this, the training needs to be factored in to some extent. And in many cases, it can exceed several orders of magnitude of your runtime or your data acquisition. And this is just another matter that we have to consider here, right? So illustrated this picture, neural networks for this particular applications are just introducing more computational complexity as we require the training of a larger set of model parameters. Yeah. So with this, I want to move on and talk about some of the applications from this class of supervised learning methods. And the simple question that I have is, well, how can we take advantage of the supervised learning methods and augment this for turbulent combustion simulations? Right? And to illustrate this, let me briefly motivate this. What I'm looking at, the simulation of a rocket combustor. This is illustrated here. This is a classical rocket engine. I think many of you are very familiar with the system. We are injecting, in many cases, liquid oxidizer and reactive fuel mixture. In this case, this is methane. And the combustion that we are observing can be highly complex. We're identifying different combustion regimes, illustrated here on the right-hand side. Each one of the color coding indicates one particular combustion regime. And in many cases, what we can use is we can use fairly complex combustion simulation models. Those models come with the expenses that they're computational rather complex, and with this, time to solution is incurred. But what we can think about is we can take advantage of the different combustion regimes by adjusting the model fidelity in such a way that we're tailoring this to different combustion problems. Right? And this is illustrated here. We're solving the governing equations. The high computational cost arises from three sources. The first one is the number of species. The second one is the scales and the chemical stiffness, which arises from the viscous and the chemical source terms. And the last aspect that I will address later on is the closure model. In many cases, those closure models can incur additional computational cost or are simply not known. So in this case, they would also introduce additional numerical errors. Right? So what we can do here is we can pull models from our existing literature, and they are quite rich. I would like to categorize them into topology-based combustion models. These are simple models which take advantage of the underlying flame topology. Many of you are familiar with the concept of flamelet type combustion models. As I said, they are computationally very affordable, but they come with a price that they lack physical expressiveness and complexity. In contrast, we can use so-called topology-free combustion models. These are, in this case, finite rate chemistry simulation models. They are fairly accurate, but they are, of course, more expensive since I'm solving a larger set of chemical species. So what I like to do here is to see whether we can combine different combustion models which have different physical fidelity, and in this case, also physical accuracy, in such a way that I can improve overall the predictive accuracy. And I want to do this only by using this in the context of the machine learning methods. Here, I want to identify a machine learning strategy that allows me to classify different combustion regimes. Right? And this is illustrated here. I'm showing here simulations of two simulations of this rocket combustor. The figure on the top is a finite rate chemistry simulation, where we're essentially solving the detailed transport equations for the species. In this case, this is the methane oxygen system. And at the bottom, this is a classical flamelet model. FPV stands for flamelet Process variable formulation. This is essentially a scalar mixing model. And what you're clearly seeing is that if you look into the temperature, the top figure is always the instantaneous result. The bottom is the mean results for temperature and carbon monoxide. you're clearly seeing that there is substantial differences in the flame lengths, right? Our flame model substantially underpredicts the flame length. We are having deficiencies in predicting the thermal boundary layer and recombination. These are all deficiencies of a flame model. And what I'd like to do is to use a machine learning driven on data assisted classification methods so that it can select different models in different regions of my reacting flow field to overcome deficiencies of the flamelet model, but at the same time reduce the computational cost of my simulation. The experimental configurations that we're considering is this TUM, the Technical University of Munich, GOX methane single element rocket combustor. This is an experiment done by Silvestri several years ago, and this is, I think, an ideal test case for our investigation. The machine learning algorithm that we constructed is shown here. We are referring to this as a data-assisted LES simulation. And what we're doing is, in the first step, is we're performing simulations using infinite rate chemistry. Then we are introducing errors, and this essentially is in process for the data pre-processing or the training of our machine learning algorithm in such a way that we can construct different features or labels from our simulation. They are based from a training feature set. In this case, this is a 6-dimensional input parameter space. And what we are obtaining from this method is our random forest, which we're using here essentially as a classifier, right? So we are doing our simulation. We are identifying the different features. With these features, we're entering our random forest. And from this, we're obtaining different labels that identify 3 different combustion regimes. And based on the local assignment of each one of these combustion regimes, we are identifying and utilizing a different combustion submodel. To go a little bit more detail, the construction of the training and the training labels and the outputs is done through this error function. This is, in this case, a maximum norm that is weighted within certain pre-coefficient. In our simplest form, all we're really asking is that we can threshold our accuracy, right, with respect to the finite rate chemistry, which in this case is our reference data set. We are identifying user-defined thresholds, and what we can really think about is for each one of the thresholds, we would essentially perform a different training set so that we have different classification algorithms available to meet certain accuracy requirements during the simulation. In the simplest form is, if I'm falling under a certain threshold in my solution accuracy, in the simplest case, you can think about the temperature predictions of my combustion model. If I'm within a certain accuracy, I'm reverting to an inert mixing model. If I'm exceeding this threshold by another margin, I'm using a flamed model. And in case everything fails, I'm using a finite rate chemistry model. And with this structure, I now have a very convenient way of this classification methods, meaning that there is no extrapolation or regression that allows me to always ensure that at the model of highest fidelity, I'm reverting back to a finite rate chemistry formulation, right? To illustrate this here, we can look to this composition diagram. In the regions of pure mixing, this is the pure oxidizer and the pure fuel stream, I'm relying on an inert mixing model. If I'm looking to conditions very close to the equilibrium, this is on this branch, I'm using a flamelet solution, and everywhere else where I have strong mixing, where I have strong non-equilibrium effects, I would essentially utilize a finite rate chemistry model. One important thing that comes out of this formulation is how do we identify appropriate features? And these are really the input parameters that we're requiring here. And since we are utilizing a random forest, we have access to the expressiveness or the physical interpretability of these methods. And this is essentially one way for us to identify features. And this is what we have done here. We used a so-called maximum information coefficient to identify some of the most selective input parameters that are sensitive to the combustion model. And from this, we identified 5 leading contributors. These are the Process variable, the mixer fraction, and mixer fraction gradient, which is essentially a proxy for a scalar dissipation rate. We identify the density and the local Prandtl number as some of the key parameters that determine the particular combustion model assignment. And we use this for the training process. Right? I want to show you some a priori results and then move on to our posteriori results. This is illustration for different model assignments. You can think about this for different accuracies that you want to achieve during your simulations. With increasing model accuracy, we're seeing that there are substantial regions of finer chemistry, smaller regions of inflamed model solutions are typically confined within the combustion core. And we're seeing also some inert mixing description, right? So overall, I think this model in this a priori analysis is quite well described. And with this, we can move on to an a posteriori simulation. What I'm showing you here is an instantaneous simulation result from this data-assisted model with an accuracy threshold of about 2%. So what we really are asking is that our solution of this data-assisted LES calculation should be within 2% of our final rate chemistry method. So this is a rather tall order. And to achieve this, we can look to these different flow field quantities moving from top to bottom. We have the temperature, we have carbon monoxide mass fraction, we have the mixing field, and this figure here at the bottom is our combustion submodel assignment. What you're seeing here in blue means that we're utilizing inert mixing. In yellow, we are relying on an flamed model, and the reddish region is in final chemistry model. What you're seeing clearly is that there are some localized regions where we are resorting to an flamed model, in regions further downstream, in regions near the boundary layer where we have a strong thermal recombination. We are recognizing, or this model is recognizing, that inflamed model is not accurate, and we would have to resort to infinite rate chemistry model. So overall, you're getting the right trend without any physical or domain knowledge, in the sense that we have not prescribed any combustion regime criterion beyond the feature input sets that we extracted from our machine learning algorithm. In the interest of time, I want to skip over this figure here. What it really tells us is that the model, this data-assisted combustion model, is embracing or bounding the final chemistry in the flamed solution. We're getting reasonable reductions in the computational cost between 20 and 30%, depending on the accuracy requirements. And overall, the model is recovering a final chemistry method based on this formulation, since it's a classical classification model, so that we are not extrapolating or violating any underlying physical constraints. I think one result that I want to show you here is, which I think is quite interesting, is asking the model to extrapolate beyond conditions that it has seen before during the training process. And for this, what we did is we trained the model for one operating conditions and then employed this random forest at conditions for which it was not trained. And we achieved this by increasing the inlet velocity by a factor of 3, so that we're getting substantially shorter residence times in the combustor, and with this we're changing the mixing characteristics. And what you're clearly seeing is that this model is still able to handle this extreme operating conditions, and it's doing this at the expense of reducing the assignment of the inert mixing and the flamed formulation by just imposing a stronger presence of and final rate chemistry representation, which you clearly see here in this regions, right? Meaning that under the conditions where our model is not comfortable assigning models of lower physical fidelity, we are essentially resorting to computationally more expensive models. This is not violating the underlying physical principle, but it essentially incurs just a higher cost. But overall, we can still assure that the solution retains its accuracy. Okay. So in summary of this chapter here is I illustrated one application of an supervised learning classification methods to augment turbulent reacting flow simulations. We're essentially using a random forest or a neural network in such a way that we are using this for the identification of different combustion regimes. This machine learning methods is then incorporated in our simulation so that we can locally assign different combustion regimes to different applications. I showed you a couple of applications that clearly this method outperforms pure monolithic finite array chemistry and flame-lit formulations. It has all of the key features that it enables the extrapolation to conditions that it has not seen. And beyond this, it recovers the overall solution accuracy. There are a couple of open challenges that I want to address in the remaining time I have. And this really has to do with how can we also now extend this framework or this model to construct subgrid scale models and extend models to more complex state equations and combustion regimes. Right. So with this, I want to talk about knowledge-guided data-driven methods, or the simple question, how can I modify my machine learning methods so that I take advantage of prevailing domain knowledge that we have very well established in our community. For this, I want to go back to our initial diagram that I showed you here, where we are comparing available data with available knowledge. And I want to mostly focus on this knowledge-guided regimes. Right? And here the question is, how can I augment my traditional machine learning methods with knowledge? And it turns out that I have several ways for doing this. This is my conventional training process. And I'm showing you here, and it's depending on available knowledge or the task under consideration, I can inject physical knowledge in the loss function, where I'm now constraining my loss function so that I introduce physical principles. This could be mass conservation, this could be energy conservation, species conservation, or some other physical principles. I can incorporate knowledge in the training and the testing data by selecting certain quantities from my existing experimental data, by augmenting additional data or targeting specific operating conditions. Furthermore, I can, in machine learning methods, extend this to have different output layers that introduce or represent different physical principles, invariants, strain rate conditions, or even modify my neural structure so that I represent different physical principles. And this is just an illustration here of different ways of introducing knowledge in such a way, either in a strong or soft constraint way, so that my machine learning algorithms obey physical principles, and this comes at the benefit of reducing overall the computation cost and potentially also rely on fewer data available for this analysis. I want to illustrate this an example of the construction of subgrid scale models that remains in prevailing frontier in turbulent combustion models. I illustrated those here in this 4 different terms. And what we like to do is we want to look to operating conditions for which I have very little information from my domain knowledge to construct subgrid scale closure terms. Right? So to illustrate this, I want to look again, stay in the realm of rocket combustion, high pressure combustion, where our available knowledge about constructing reliable subgrid scale models is essentially very, very shallow. Right? So we're looking to a liquid oxygen, gaseous methane operating condition, and we can ask, how can I use machine learning techniques here to extract a physically consistent subgrid scale model that is reliable for this high pressure operating conditions. To illustrate this, we are generating in the first step data. This is in DNS with about 128 cube domain, illustrated here. This is in spherical blob of liquid oxygen embedded in a gaseous hydrogen at a pressure of about 100 bar. This is exposed to a turbulent environment, and with this, we're seeing this diffusion, the mixing, and ultimately the combustion process. What we would like to do is to take this set of data here that we're generating, in this case for 2 different downcaler numbers, and construct a subgrid scale model for the turbulent stresses. In order to do this, since we're primarily interested in LES simulations, we are applying filtering to the systems at different filter thicknesses. which is illustrated here by delta. And from this, we can now construct the subgrid scale stresses. This is an exact form from this DNS calculation. And ultimately, we want to find a functional expression that relates the subgrid scale stresses to, instead of input features, and this is the filtered velocity, the filtered gradients, and the second order derivative. And we try to identify this input-output mapping through a data-driven technique. We're using, again, a random forest for the reason that we take advantage of the expressiveness and the physical interpretability, which I think is here really a key asset of this methods, and we fully embrace this in our application. I talked about the random forest already, so I want to skip this in the interest of time and just jump right into this model predictions. One key attribute of this is an Pearson correlation, which essentially allows us to assess the sensitivity of different quantities to the training data. So what it really means is we're asking which one of the features is most important for different applications and how accurate is each one of these systems. So what you're seeing here in this case is two examples. In the first figure shown on the left, you're seeing that the training data and the test data is taken from the same simulation. So we are essentially testing the in-distribution of these models for different filter sizes. What you can clearly see is that, yes, with increasing filter size, our correlation reduces. That means our expressiveness or accuracy reduces. The more interesting aspect is that if we are training for a dumb-killer number of 10, but testing for an out-of-distribution example, and where we're really applying this to substantially higher dumb-killer number conditions. And here you're clearly seeing that instantaneously our model loses accuracy. So we're dropping the correlation coefficient, and with this, we're losing essentially an impurity in this case, meaning that our model lacks expressiveness or accuracy. And this is, again, one hallmark or one prevailing issue that we as community need to address, that machine learning methods that are trained for one condition can be generalized to conditions that it hasn't seen before. Right. So the next step is what we like to do is to now construct a combustion or a subgrid scale model. For this, we seek a functional representation. This is an algebraic expression of the subgrid scale models. We're identifying features. They are denoted by X. As I said, we're pulling from different distributions, velocity gradients, and second order derivatives. We have coefficients beta that we would identify in such a way that they obey sparsity. Sparsity is a really interesting and powerful tool so that we make the models as compact as possible. And of course, the function f is our model subgrid scale term that we would like to represent. So in order to do this, we're first constructing a nonlinearity matrix, which is a higher order combination of different pairwise representations of these polynomial functions. We can then solve for beta. These are our coefficients through an optimization step. We essentially want to minimize this functional f. This is our subgrid scale term projected onto this product of our polynomial basis and the coefficients. And what we like to do is we introduce sparsity here by introducing a Lagrange multiplier, which essentially forces us to minimize the number of weights or biases. And ultimately, what we're getting out of this is two pieces of information. Which one of these coefficients in which polynomial order is most relevant, and at the same time, which one of the pre-coefficients we have to use in order to construct the subgrid scale model. Okay. So to do this, again, we're relying on this sparse regression formulation that Photon employed here. And we're seeing that really for these applications, there are primarily two key parameters of importance out of this 9-dimensional parameter set. This essentially allows us to reduce dimensional complexity. And what you're seeing is, well, the velocity gradient is a key parameter, and in addition, we also identified that the velocity and the scalar velocity can play a key role here in the system. But ultimately, what we're really doing is we're reducing this initial exposed parameter set to a lower dimensional manifold, and from this constructing a rather compact form of the subgrid scale term. Once we're doing this, we're going to the same procedure of the weighting. Those coefficients shown here in this red box are this beta coefficient that we obtained from this sparse regression matrix. And ultimately, we are constructing this rather elegant subgrid scale model, which essentially takes velocity gradients into consideration. These are pre-multiplied by filter width and density. And these are parametric coefficients that are constructed here for the diagonal subgrid scale coefficients. And if you're comparing this with a well-established model from Clark and Furtziger, we are identifying that this model approximately recovers the Clark and Furtziger formulation, which was essentially derived from a Taylor expansion, I think back in the late 90s. Right? So here, I think, again, we are able to identify or introduce physical knowledge or extract physical knowledge and tune parameters or adjust parameters subject to specific combustion applications in such a way that they are trained and obtained from this available data set that we considered here. Right. So in summary, we constructed an interpretable machine learning model for subgrid scale closure models. And this is, I think, an interesting demonstration that data can be used to construct physical information instead of using them for pure regression analysis, which is commonly done for perhaps regression models. Here, again, for this particular application, we relied on a random forest as it provides expressiveness and physical interpretability that we utilized quite extensively here to real important input features. And the random forest can then be combined with a sparse symbolic regression to discover in physical model as illustrated from the rediscovery of this Clark and Furtziger combustion subgrid scale model. The last section that I want to discuss here is open research opportunities and research needs. And in principle, we can identify several open research issues. But before we do this, first have to recognize that we as a combustion community have made some impressive progress on embracing various aspects of machine learning, simple regression, feature detection, dimensional reduction, to more complex tasks that include the generation of subgrid scale models for the design optimization and so on. So this system is prevailing, yet I think there are still a couple of open research opportunities that could help us to really accelerate the use of machine learning techniques for combustion applications. And identify 6 relevant parameters. I want to talk mostly about the first one here, and this really has to do with benchmark data. I started my presentation by recognizing or making this bold claim that there is a large amount of data available, but it comes from heterogeneous sources in its current form widely distributed, meaning that access is somewhat limited. And this is true. What we like to do here is, or what I like to do is, and call from to the community to help us really accumulate this data set in such a way that this is accessible for our entire community. Beyond this, there are several other challenges, and they really has to do with the particularity of combustion problems. Most importantly, we as combustion community embrace this concept of physical interpretability. We can utilize equations that are well established, and we have a fundamental understanding. This is in many cases lacking if we're using traditional machine learning methods, and there's clearly a need to improve the interpretability and explainability. I try to touch on a couple of aspects during my presentation here, but I think there is clearly more opportunity to do this. Another issue that is unique to combustion or scientific applications is the quantification of uncertainties. Combustion, by definition, is associated with safety, with very sensitive quantities. If you're looking for propulsion applications, if you're looking to safety critical engineering problems, there we would like to have implicit understanding about the uncertainty that is accompanied with a particular combustion model. And I think there is clearly opportunity to make progress in this area, so that we are not only generating a machine learning methods or model, but we're also associating this model with certain uncertainties. I think this is quite critical just to introduce confidence in the combustion modeling. I showed you a couple of examples where actually machine learning methods fail quite dramatically if we are applying this to conditions that are out of distribution or that our model has not seen. I showed you, in fact, 2 applications here. There is, for us as a community, quite a lot of opportunity to extend these models beyond their systems. And one pathway could certainly be the knowledge-guided, data-driven methods, where we're augmenting missing information with physical knowledge. And I think this is, again, one really exciting research opportunity to make progress. In this conjunction, integration of domain knowledge in combustion ML is helpful to tackle the previous point. And the last aspect that I want to mention here is computational complexity and accuracy. We talked about models that are fairly complex here. I'm showing you a rather complex CNN for classification and regression. Many of these models can have upwards of 1 million, if not 1 billion parameters. And especially if you're thinking about foundational machine learning methods, those systems can be quite large. And it would be useful that we as a community come together to construct these models together so that we can take advantage of different forms of initially pre-calibrated or pre-constructed methods, right? I want to briefly expand on the first aspect on benchmark data and metrics. And here we can take some knowledge from other communities, mostly from the computer science image recognition community, where this community has over the recent years been extremely prolific in constructing large sets of databases for image detection, for other feature detection and applications. And I think there is clearly opportunity for us as community to learn and embrace similar concepts. So what we're seeing here is ImageNet is a very well-established database, which has influenced various aspects of machine learning in image recognitions. The key point here is that this contains about 15 million images. If we are embracing for similar complexities in our combustion community, I think this would be a really interesting opportunities, but most likely this is not achievable since our data are certainly more narrow, more localized, and more specific for specific applications. But in general, machine learning techniques benefit from data, and this is really a key message. And then the question is, well, how can we emulate this? And as a matter of fact, there has been some forays done to some extent in our community. I want to here illustrate the Johns Hopkins turbulence database. I think many of you are certainly familiar with this. This is a database which contains 9 discrete DNS configurations at a very high accuracy. Each one on the total database is about 500 terabytes. And this is one example where we have data established on a common database utilized, but this database is not meeting the requirements for machine learning because of the distributed data for different applications. And then the question is, well, how can we do this? And why Tom came up with a cool idea, this is essentially embraced here in this blast nest. This is a community-wide web platform or framework that allows us to collect data from different contributors in a centralized database, but in distributed data acquisition system. And we're using existing community services. Consists of 5 steps. Step number 1 is the collection of the data, and this is locally done. We can compress them or acquire them. And here the idea that we are putting forward is that we're using existing open source commercial or public databases in the form, for instance, of Kaggle, which essentially provides about 100 gigabytes of data, free data access for each user. And this is essentially one proposition on how we can, as community, accumulate large data that is accessible to the entire user base. Step number 4 in this framework consists in the consolidation of this Kaggle databases into a metadata base, and then expose this to the different users who are interested in accessing this. So this is essentially taking the principle of an ImageNet or an open community database, but recognizing that our scientific data that we are dealing with is much larger, much complex. And there we have to essentially introduce an intermediate step that is requiring compression or in weakly distributed data net so that we can, as community, access this to a wide range. So what is available currently on this is that we are envisioning that we're collecting about 100 different non-reacting and reacting flow field configurations. This database is currently available and populated as we speak. We provide tutorials, shared user access, and machine learning samples for these applications. It contains metadata, and most importantly, it acknowledges users that contribute to this database by essentially fair attributions to co-authorships that ultimately we as a community want to establish our database, our scientific database, to accelerate the scientific discovery and development of machine learning methods. And I think this is potentially an interesting proposition for us as community to make some forays in generating data, which is essentially at the foundation of machine learning methods. Well, let me skip over this here, and with this briefly summarize what I talked about. I provided you an overview about various aspects of machine learning techniques. I have to start out by really recognizing that there has been substantial progress done on different aspects of machine learning methods, embracing them, testing them, evaluating them, and applying them to various combustion problems. There remains further opportunities that I addressed in regard to the 6 different topics. What we certainly have to recognize is that combustion science and engineering has been traditionally based on physical principles, and we certainly should embrace them and continue incorporating them into machine learning methods so that they will not be purely data-driven, but take a form of a knowledge guided or data augmented principle. One thing that we have to recognize is that we have certainly a much taller order to deal with in our combustion field, for the reason that we are dealing with safety critical principles, that we are retaining physical constraints as well as uncertainty requirements in our applications. And this makes it just a little bit more difficult to identify machine learning methods that are tailored for our applications. Of course, I didn't have time to talk about all aspects, and here we wrote in a review paper that I encourage those that are interested in to expand further, since it provides more applications from different fields. This is including system level applications as well as safety critical problems. And with this, let me thank you, and I'd like to acknowledge Wai Tong and Ashwin, as well as the entire research group, which has been instrumental in contributing to this work. Thank you.
Thank you, Professor Ihme. Thanks for the wonderful talk. I think it's very educational and encouraging. And we do have some questions from the audience. The first one is from an anonymous audience. He asked, have you thought about using convolutional neural networks to extract information of topology in the input data? He thinks it can be useful for some of the examples.
Absolutely. Our group per se has not done it so far. We use convolutional networks for dynamic flow field predictions, but we have not used it for feature detection. But I know there's quite a bit of work done in the group of SERPACs as well as NREL to take CNNs to construct combustion models from flow field simulations. CNNs are also used for extracting information from experimental data. I think there's Hubert Georgia Tech who made some really interesting contribution to this. Yeah, very good suggestion.
Yeah, and we have another question from Huang Wei. He asked, thanks for a nice presentation. How is the maximum information coefficient determined? It is used to identify the significant features. Thanks. I think it's about the Fleming progress variable, like the model selection part. I think the main point is about the maximum information coefficient.
Yeah, so here we are essentially extracting this maximum information coefficient from our experimental data. In the simplest form, you can essentially look to a correlation coefficient that maps the input to the output. And this provides us here essentially one very established result to identify which one of the features are key critical for this application.
Okay.
Okay, thank you.
Okay, and we have another question from Dr. Ling Guo. He said, thanks for the nice presentation. He's Ling Guo, a postdoc at Norwegian University of Science and Technology. He mentioned your university website indicates you do biomass combustion. He is wondering whether you have applied the machine learning methods in particle-laden reacting multi-phase flows. For example, CFD simulation of woody biomass particles in gasification or combustion progress. He did some experiments during his PhD studies. The laser measurements showed the dynamic and thermochemical conversion histories of woody biomass particle in train flow gasifer were very complex and hard to model in the Lagrangian phase. Usually it's anisotropic fiber structures and irregular shape of the biomass particles. He is wondering if you could be so kind to provide some insights or educate the guesses based on the experience.
That's a fantastic topic, and I think if we are looking to biomass combustion, we're looking to wildfire applications. What you're really seeing is there's so much spread in the combustion response where we have very little data, right? So very little physical knowledge, and this would be, I think, a fantastic application where we can really embrace this data-driven field to make some forays. Simply for the reason that our knowledge on biomass combustion, pyrolysis, smoldering, coking, soot formation is, I would say, very rudimentary and still based in heuristic principles. I think enormous opportunities to specifically answer your question. We have not used any machine learning methods for this. What we have done mostly is the characterization of biomass combustion using tomographic reconstructions. Currently, the data set that we're using, each one of the data sets is very large, but we have not enough diversity so that we just like available data for doing this. But I think this would be, another really exciting field to build up knowledge based on this data-driven methods by acquiring a large set of data. Yeah, great suggestion.
Okay, thanks for the answer. Another question is from Professor Zhi Chen from Peking University. He asked a question about what could be a good configuration for constructing database for turbulent combustion. For example, a statistically planned Bremens flame in homogeneous isentropic turbulence is probably a good starting point. But still, we have too many parameters like Rayleigh number, depth number, and many other numbers. And all of this without mean shear or any other practical relevance. What are your thoughts?
Yeah, the simple answer would be everything above, right? So what I mentioned is also in the context of this blastnet is what we really have to think about. We need diversity, right? So, and there is no wrong or right database as long as we're exposing our problem to as many different data, right? That our machine learning methods have seen different data. What I would probably think about is to come up with some hierarchical structures. And we're currently thinking about simple flame configurations, so the class of homogeneous systems where our community has generated quite substantial amount of data. We have done the same for shear-driven data or statistical stationary flame configurations. If you think about this entire class of premixed flames, turbulent premixed flames, I think this would be a fantastic set to expose to our community database so that we can successfully build more and more data. So short answer is any data would be good. If you're comfortable generating data on a simple flow configurations, I think this would be a great contributions. And then we can certainly build up once we have an existing nucleus of different data. Right.
Okay, and we have another question from Anusa Raman Kuti. He thanks for the wonderful talk on the application of machine learning on combustion. He is an upcoming combustion researcher from India, currently doing research studies at IIT Madras. He was wondering how to apply machine learning-based models for spray combustion with current Lagrangian methods that we currently use. Could you provide some thoughts on that?
Yeah, I think if you're thinking about spray combustion and simple or a remaining issue that I'm seeing is really the heterogeneity of the particle field. So classical theory considers isolated droplet combustion or group combustion system. But if you look into engineering applications, you're typically spreading this entire category. So what I would certainly find very interesting and really impactful for us as in modeling spray combustion is to address the heterogeneity of the spray field, particularly in the interaction of this dilute and dense regimes or this heterogeneous systems and the context of the interaction of the spray with the combustion as I think a really exciting modeling challenge. And with this, you could embrace classification algorithms, unsupervised methods on identifying droplet clusters in the context of spray, and ultimately map this back to combustion regime. So yes, very rich field of applications where I think our physical knowledge certainly lacks fidelity to describe this complex spray regimes.
Okay, yeah. So I have two general questions from my own experience. The first experience is when I learned something in machine learning, I feel it's quite easy to reproduce their results because they have the same infrastructure. Like they have the TensorFlow, they have PyTorch, and they also share the source code and the data sets. That's why it's so easy to reproduce and learn the machine learning techniques in computer vision and other related areas. But I feel it's kind of hard in combustion area because we don't have a common infrastructure in terms of the CFD code. So to what extent do you think it is necessary, like we need to build not only the data sets, but also the code repo so we can reproduce or test the model on the same level?
Yeah, that's a great question, Tianhan. What we discovered is similar challenges, and the reason we address this by essentially constructing an GitHub to provide some basic tutorials just to ensure that data is or the results are reproducible. For more complex applications that are published in the research literature, reproducibility is somewhat limited, and this comes for two reasons. Number one is in many cases the hyperparameters, the model is not exposed, it is not accessible, and in many cases the data is not available to reproduce this. I don't think we need to have the source code for the generation of the data since we're working on the available data, but getting access to the data and to the model is essentially a key parameter, right? For demonstrating reproducibility and then building up knowledge, common knowledge within our community that we can build on, right? So it is not particularly useful if you're generating your machine learning model for regression. I do this, and another 5 or 10 people there because it is redundant. And I mentioned it is computationally very expensive, and we can build a common database, or you can call this a foundational machine learning model, where I think we can really build up more capabilities and knowledge, right? And I believe that this is currently one challenge that we will be overcoming as a community, but it takes a little bit more time and focus from us as a community.
Okay, thanks for that. And another question is about the training and learning. So from my experience, I feel machine learning has a very rapid development, and the information and knowledge is so distributed. It's very hard for me or for my student to learn systematically. However, combustion is also a hard target to learn. Like there are much physics to understand. So do you have any suggestions, like how can we train students or teach them in this interdisciplinary research?
What I'm seeing here at Stanford is that I would say a lot of our students who are working in this machine learning, they're taking essentially courses, fundamental courses in computer science on statistical methods, on classical machine learning methods, but they are mostly inspired by data analytics, image recognition, feature detection. And then making this connection from this classical data analytics to the scientific community is another challenge there. And we address this by specific training courses, by having collaborative efforts with the computer sciences community at Stanford, where I think we are making inroads in this. It is still not there where I like this, but you're absolutely right. The field is diverse, and it needs a domain expert in combustion and a domain expert in machine learning, right? And what I hope is that we can bridge this by making more of the standard methods available to our community, so that not each student writes its own CNN or utilizes its own CNN, but this becomes essentially tools, right? Pretty much in the same as in CFD tool. I think many of the students that are here on this call certainly using some sort of open source codes instead of writing their own CFD solver. And I could see the same, that we're using existing libraries, existing tools, and building up capabilities from there.
Yeah, I think that's a good idea. And maybe in the future, we should have some like TNF workshop, just similar to TNF workshop, and another workshop for machine learning, or maybe some summer school, maybe at the like Turbulent Research Center or something like that, that can really help us to educate the students and ourselves as well.
Yeah, that's a great suggestion. Yeah.
Okay. Yeah, I think that's all the questions I saw in the Q&A session. Professor Huang Wei.
Yeah, I don't have any more questions. Yeah, so thanks, Matthias. Thank you very much for giving us the insightful talk.
Thank you so much for inviting me.
Yeah. So any more questions from the panelists? Okay, so whether you have questions?
Oh, it's stretching it a little bit, but actually I just have a very brief questions for Matthias, because I think in all these discussions, we are talking a lot about simulations, results as a database input. So in your opinion, like I suppose experimental results will also have a placing in the platform that you're trying to set up, but do you see any challenges in trying to incorporate such data sets as well?
Per se, I don't see this, Wiley. If you're taking it naively, data is data, and if you don't know where they came from, it remains data, right? But there is different classification, right? So what you know from your CFD simulation, and right, Wiley, you know this better than I, you have just access to all scalar fields, to multiple different gradients, and experimental observations just lacks this richness. And in many cases, it also comes with certain uncertainties that we have to incorporate. So this data set will be different. It will have different characteristics in terms of the uncertainties, in terms of the distributions, and also the expressiveness, so that we have to be careful on how we are understanding the integration of different qualities of data in our machine learning methods. Right?
Mm-hmm. Yeah, that's the only thing that I actually wanted to ask you. Yeah.
Okay. Any more questions? Okay. So if no more questions, I would like to encourage all of us. Okay, open the camera and thank Matthias again. Okay.
Thank you so much.
Yeah. Thank you. Okay. Thank you. See you next time.